So our demonstration of the basic reference concept is over. So I'm just going to say, typically, you can clean your build to remove some temporary files and just say file close solution to make sure that we're no longer handing over this specific location. And what I'm going to do, this time I'm going to say open project solution and reopen the, let me see, where was I? I was somewhere here. Right, so this is where the project existed. Okay, so week 9, we finished by looking at the concept of a stack. So if you have a copy of it, you can reopen your project. I will reopen this project on my own and load it, and let's take a look at where we left off and what we have done. Okay, so let me actually close all files so that they're not, distracting our view of anything, right? And instead, I'm just going to say View Solution Explorer or view your manager window in code blocks if you're using code blocks at home, right? And on the list of source files, I see 2 files. One is main.cpp. I already know what's inside, right? There's like some version of a main function inside there. But there's also InStack, which basically the implementation of the stack. And once again, let me close this. I wasn't intending to open it, right? But part of it is, and this is where I'm going to start, is that you remember that I started by creating the header file for the concept of an integer stack. So if I want to refresh my memory regarding what that concept was, here it is, right? So there's a header file, right? We have the header guards, as always, and we have the declaration of this concept named class InStack. This is a stack of integers. Just a reminder, remember how the stack concept works, right? So we said that a stack is a container of temporary objects, and what it does is that it acts like this type of container where you can store things of certain type, and the only access to the container you can access to the top level of this container, and you can basically have it removed from the container, and then of course you get access to the next element in the container, right? So you can get its value, or you can remove it from a stack as well. And of course, if you instead decided to add another element, that's fine. You can keep adding elements to the stack, and we already made it in such way that its capacity, the possibility of store more things, dynamically growing, right? So if all of a sudden we realized that we were out of space over here, if we had the reserved space for 4 elements, we can say duplicate it, and then the next time we push another element, its capacity is growing automatically, and we make it larger, and we can keep accepting more and more and more data into this, right? So this is the concept of the stack, and so let's take a look at the actual stuff that went into it. So the header file contains the declaration of class stack, which begins with a class, and of course us having this class introduced to the compiler does not create any stack objects. All it does is basically tells the compiler, we would like to have a concept of the stack. We would like to give it a name in stack. We would like to, this is some internal stuff that is being managed in terms of the data inside the stack, but we would like to provide user with interface which involves a constructor, which is basically default constructor. You just can create the stack. The destructor, which is invoked when the object goes out of scope. Push, pop, top, and size. Okay, so for now, just the simplest possible version of what the user can do. If we open our main function, what happens is that we begin to use the stack, right? We begin to use the stack, and now I can again go switch to show this code side by side. Right, so right here, first thing that main does, it creates a stack object. Just like I can create integers, now I can create my InStack instance of my InStack class, which is an object in memory, which will contain all of its data internally. Right, and then I can start using it. I can say push, push, push. I can say pop. I can also access the top of the stack and display what's there. And I also have the size, so I can keep track of the size of my stack. And for instance, if I wanted to empty it, right, over here I could have written for or something like this. I could say while, right, for as long as stack.size, right, stack.size is greater than 0, for instance, right, I could just say stack.pop, which removes the elements from the top of the container, and this loop will continue to execute for as long as size is not 0. As soon as size becomes 0, we move on, and the program will finish, right? So that's where size becomes obviously useful, which allows us to simply, essentially, make stack empty. Now, when we use the simple interface, what's hidden here is that, number one, when you declare a variable of type InStack, its constructor is invoked, okay? So this constructor function, which is designed to get invoked anytime you construct the stack, it will be invoked, and it will do something internally with an actual object. Likewise, when we say return, right, or when this closing brace for the local scope of the main function closes, and we really get out of the scope, and the stack has to go away, it will be destroyed, and upon that event, upon return, and before we actually return, a destructor function is going to be invoked for our stack. And it will do something to free up memory that was dynamically allocated as a result of us populating this container with values, right? So before we take a break, let's take a look at all right, so here's our Solution Explorer again, and this is the implementation file. Again, I'm just going to right-click and say move to previous tab group to display it side by side. And this is where we can see what we have done to implement the functionality of our stack. So before we look at this, let's now get a closer look at the actual data members of our stack, like really the data that it has. Because remember, it's good to draw diagrams like this, but in reality, what happens is that our memory is made up of like zeros and ones, right? So we have some values in memory that look like this all together, right? So if we were looking at memory through some kind of a special type of microscope, all we would see in computer memory is like zeros and ones. And depending what is the context of that 0 and 1, it can be a character, it can be an integer, or it could be an executable instruction that CPU understands and executes on our behalf, right? So our stack is somewhere in the midst of this, the sea of zeros and ones, right? And this is our stack, somewhere occupying memory and containing some data, right? So we need to really analyze what these zeros and ones are, and for that we just look at the content of our stack, and we say that our stack is actually made up of the pointer to an integer, right? Memory block is pointer to an integer, top of stack is an integer, and capacity is really the physical size of that memory block, right? So when we say we want to have a memory block, we have a capacity internally describing the size of that memory block. In other words, what we see is this, right? So our stack, if we try to picture it as an object, I don't know, maybe draw it more like a 3D thing, what we have there internally, we have a pointer to an integer, right, which is called memory block, right? Then we have an integer that has a name top of stack. I'll just simply say top of stack, something like that. And finally, the third integer is called the capacity, right? And that's pretty much all we have inside this box. When we want to store elements, the elements are actually stored in a dynamic array of integers, right? In a dynamic array of integers, which is allocated elsewhere by the new operator, if you recall, right? And this dynamic array of integers, we use, the capacity tells us how big this block is, okay? But at the same time, the top of stack is not a pointer, simply just an index that says this is the current element, which basically specifies where the top of stack is. So this chunk of memory, block of integers, is managed by new and delete, right? So we say that we have this free store memory manager, which we access by calling new and delete. And if we want to allocate memory, we call new and say, this is how many integers we want. If we want to return memory back to the system so that we don't have memory leaks, we have to say delete. If we said new, someplace we have to say delete. Java programmers don't have to say delete because Java does that automatically. And that's what Java is praised for, because it has this automatic garbage collection. In C++, when we use this raw stuff, we have to remember that each new must be matched to a delete call. So let's just finish a quick overview of this code. This is our constructor. The constructor basically says the top of stack is 0, and I think that it also and then it calls allocate memory, and it wants to allocate memory of default size. Allocate memory is a member function which calls new, right, and says this memory block, right, will be pointing to this many integers, block size. And of course, right away it populates the capacity of the block size that was requested, and we also print some tracing messages that say that the block size is such and such, such and such in size. The destructor of our object is trying to be careful not to leak memory, and with the destructor of our object with the tilde in front of the name, that's the name of the destructor, its implementation says delete, and it's using this curious array syntax in front of memory block, but that's just a technicality. Basically it says, okay, free manager, we no longer need this block of memory, you can take it from us, we don't care anymore. In fact, our entire object is being destroyed. Someone found a way to say, you have to go out of scope, we're no longer going to be using it, then of course we say delete, right? And we have some other implementation details, like for instance this reallocate memory, which you have to go to the prior version of our demonstration. You can view it on YouTube where we post our lectures, right? And then of course we have the push, and push automatically checks the capacity. As soon as the top of stack reaches the capacity, we essentially reallocate memory and say we would like to occupy a different and larger like 2 times larger block of memory, and then we're free to continue using it by saying, let's store the value and keep incrementing top of stack. The next time, if push is called, and again we reach the capacity, again we will reallocate the memory, so we will throw away the old memory block, allocate larger memory block, copy over the old elements to new space, and let the old block go away, right? In fact, the rest of the implementation is trivial. Pop simply decrements the top of stack indicator. The top simply returns the dynamic, just goes and returns the integer from that dynamically allocated memory. And the size simply is the same as the top of stack, and we just provide that information to the caller. All right, so this is a very quick overview of what we had last week. And then we would like to move on with this set of ideas to say what else should we do with this concept of InStack? Is it free of bugs? Is it safe to use? What concerns should we have? So that's the set of topic of today. So unfortunately, we took more than an hour just to get to where we were, and this is very typical in programming. It requires some time to warm up before you can become productive again, and before you can finish your day. You also have to cool down and make sure that you document everything and save everything so that you don't lose any of your work, right, and so forth. So anyway, so let's take a break.